Hey everyone. I just wanted to tell you about a pretty cool toy I have here and some of the fun things you can do with it. SDR stands for software defined radio, and like what I like to think about it is kind of a sound card for radio, right? It takes samples of voltage and turns them into numbers and sends them to your computer, and you can decode them. Or with some devices, you can go the other way to transmit. RTL is this like nickname for this chip, one of these Realtek ones, originally intended for TV, these little devices to watch TV. But these hackers have figured out how to put them into these little consumer units, and they're really cheap. You can get them for $10 or so. Yeah, they're really fun. On one side is USB, right? You plug in a computer. On the other side is an antenna. And there's this really awesome application, GNU Radio, written in C++, and you can do tons and tons of things like decode GPS and airplane beacons and everything like this. But this is not what I want to talk about today, actually. I wanted to try to this is like millions of lines C++. I want to do like the simplest possible thing to try and do something useful from this. And it was even easier than I thought. So yeah, the first thing to just know about this is that it's a little bit different than taking audio samples, right? Because the frequency is so high, it would just be too many numbers. So we need to have a local oscillator and mix that with the radio signals, right? And we actually mix it, the local oscillator and also local oscillator 90 degrees out of phase, multiply those with the input signal, and we get these two new signals, I and Q, in phase and quadrature. And then if you plot them on the right there, you have these things called phasor diagrams. And the idea is that you treat them as complex numbers, and the math works out really nicely. Yeah, so the thing to know about FM radio is that you take the amplitude of your audio signal and use that to encode the frequency of your carrier, right? If we're thinking about our phasor diagram, frequency is just the change in phase, right? As the phase is changing, the rate of its change is the frequency. So you can kind of think of the phasor as like spinning around in one direction, and that means that it's on the upper side of the amplitude, and then it slows down and spins the opposite way, and that's the lower side. And you can kind of think of that as like a negative frequency, which blows your mind a little bit, but in this case, it just means it's below the local oscillator frequency. So what I did was write a Perl script, and that's just the way I roll. What it does is it takes those I and Q samples and turns them into complex numbers. And then the couple of useful things to know about the complex numbers for this is just that if you multiply complex numbers, you're adding their phase angles, right? And if you take the conjugate, that's like flipping the phasor around, that's like negating it. So adding the negative, you're subtracting them, right? And then all I do is just kind of shift the previous one over one so that you're figuring out the difference between each sample. And then and then you have the actual difference encoded as the new phase. And you extract that with the argument, right? And the thing is, you don't actually care about the length of the phasor at all. That's the cool thing about FM, right? So there's no like fading or anything like that. And then my script just does a tiny little bit more, just turn it into like floats and so forth, and then send it to the audio card. And that's really it. It's a 20-line Perl script or something. A little bit of low-pass filtering too. But I'll just let you hear how it sounds. Oops. Plug that in. And I'm just literally running that. Thank you very much.